Give me a second. Is it on the right one or is it flipped?
We're at the first slide.
Oh no. It's not where I want to be. It's not where you want to be. So many slides. I want to be here. That's where I want to be.
Perfect.
Okay. Good. Welcome back. Hope you all had a nice coffee. I found mine. I believe moments ago I was here, right? Good. Now my voice is even stronger and angrier or something, louder, as I'm drinking my coffee. So I'm going to move on to the next section here. We're talking about ways in which these models are different because of SARS-CoV-2. And I've already introduced on the left this notion of the basic reproduction number being 3. We have 3 of these 9 individuals are going to be infected, and that would spread. And you can have a herd immunity threshold in which 2/3 of the individuals, and in general, it's 1 minus 1 over R naught number of individuals are infected, and then you don't have an increase, and you get to a point of decrease. But there's another way, and this was the other thing that was really missing from the early models, is that just because you have a peak doesn't necessarily mean that we've reached, in a fundamental epidemic sense, the herd immunity threshold via susceptible depletion, meaning it's possible that you can get to a point where one infectious individual on average only infects one other person, but for an entirely different reason than susceptible depletion. And that reason can be classified as awareness. So in this particular example, let me see if I can make this even smaller, just so I can have more of the screen. Is that blocking less of the screen? I felt like it was blocking the screen.
I'm not sure we saw what you did.
You don't see the floating controls?
No.
Okay, good. So in this example, you have one infectious individual, but you can also see there's this D for death. In this example, unfortunately, one of the individuals who had previously been infected died, and therefore individuals being aware of the risk start to change their behavior. In the herd immunity case, there were still 3 arrows, but 2 of the 3 were wasted due to the susceptible depletion. In this example, now there's only 1 arrow, which is meant to say that when people are aware that bad things could happen if they get infected, they may change behavior, reducing interactions, even if transiently. And that reduction in behavior rather than susceptible depletion can lead to having an R effective of 1. So if I were to go back, and I will show you more in a second, but if you recall that R naught was the product of beta Ti S over N, right? Where we assume S over N is about 1, and that R effective, the same thing, is beta Ti. Sorry, that Ti went crazy. It doesn't matter. S of T over N. This we think of as just equal to 1, but this can be less than 1. So in the herd immunity threshold, it's this that's dropping R effective down to 1. Because beta Ti is considered the same, and you imagine that people don't change their behavior. If it's common cold, they're not really changing their behavior that much. So this thing becomes the same as before. It's this part. But it's also possible that S of t still remains close to 1, and awareness is changing this, right? Or even in some ways, not the period of infectiousness, but the period of relevant infectiousness, if people start because they identify symptoms and stop going out. So awareness can lead to R effective 1, even as S of t is close to N. And that's really important. What does it imply? It implies that if people revert behavior, there's still a whole bunch of susceptibles and you can get another wave. We had worked on these models before SARS-CoV-2 came out and had already built a model, and I won't go into all the details of how it works because I'll show you a more updated version. And this is 2019, and this is why we were already writing problem sets based on them. Because we were aware that at the start of an epidemic, things can look the same, but if in the long term people are aware that there's harm and start to change behavior, the final size, or at least the near-term size of the outbreak, can be much lower than that expected based on R naught alone. So in this case, if there's some linear distancing or nonlinear distancing, the final size of the outbreak can be 100% or more overestimated. In other words, that these peaks don't have to go up to reaching a cumulative infected of 80-90% in an initial wave. They can be much, much, much less because people change behavior very rapidly, even faster than the susceptibles can be depleted. Folks get that concept? You give some nods, or you get the idea. And this also means that these forecasts can make big over predictions, and then you get the response of the media, which says epidemic models are wrong, they're sort of they're over predicting outcomes, and people start to ignore them. But in fact, the real message of this is, insofar as people are aware of outcomes, they'll change behavior. They may lead to lower near-term outbreaks, but then people may forget about that in the future, and that's what we started to explore in a model that we put out very early in the pandemic. And this model takes a susceptible, infectious, and then splits the outcomes into a recovered and a fatality pool. And without this section, I'm blocking my own screen, which is insane. Without this feedback, this would be the standard SIR model where people are infectious and they recover. Infectious individuals come in contact with susceptible individuals, leading to new infectious individuals. I'm just going to add this one component, this awareness feedback. And the idea of this is that people are aware of new fatalities or potentially cumulative fatalities, either through short-term or long-term awareness. And that will act as a negative feedback on transmission because people will change behavior. And this is irrespective of even policy change. Different countries had very different approaches, whether it was very top-down or bottom-up. In most cases, people started to change their behavior before policy changes happened because they saw what was happening, whether it was in the United States and New York, or in places where there was acute spread. So awareness began to lead to changes in behavior even before the governor or state officials made changes. How do we build this schematic into a model? Here I have the schematic on top. Here I have now a version of this with an exposed class. So I have susceptible individuals, and this dot represents a shorthand for the derivative with respect to time. And you see we have minus beta SI, and I'm going to ignore this component here below for a moment. People come into contact with infectious individuals, they become exposed. There's some incubation period in which they're exposed but not infectious. They transition to becoming infectious. Then they transition at some rate gamma into either a recovered class or a fraction of individuals who are eventually, we're going to categorize them, even though obviously this happens in the future, that eventually are going to be hospitalized and die. And then we have a fraction of individuals who are eventually going to die of this disease. They go through a period of hospitalization, and then there's a fatality pool. This is a standard model, which one can use based on these rates to predict things like timing and new entries into hospitals and so on. The difference here is that the force of infection is going to be modulated by this term, where delta is going to be the fatality rate, this D dot. And it's just hard to write D dot, so I'm writing as delta. And there'll be a critical level of fatalities, so new fatalities in a week. And if the fatality rate is much below that, this term all goes away and we get a standard model. When this term is much higher than this critical awareness level, where the nonlinearity shows up in this K, then people realize there's a lot of local transmission in terms of severity, in terms of fatalities, because it's really the fatalities and the hospitalization that led to lockdowns, not the transmission in and of itself. And so when this is much above delta C, this critical level, then there will be no transmission. People will reduce their interactions. What do these dynamics look like? It turns out this is short-term awareness, where this, I've written this in terms of, there should be a dot here. This is the same notion, but just, anyway, these are death rates. I'm sorry for the lack of a dot here. Here is the critical level in terms of a state of about 10 million, about Georgia, deaths per day, about 50 to 75 deaths in a day, right? Which if you project over to a month, is getting to be quite a high level. Right? So here we have a dynamics that would take place in the absence here of long-term awareness, where you get a peak and people are aware because there's such high levels, they start to reduce their interactions. But when it goes below this level, then it seems like things are getting better, and you actually get a second wave, and even a third small wave before it goes off in this sort of long shoulder. These are the dynamics of this one individual case with no long-term awareness. This is just in this sort of short-term awareness case. And when we add long-term awareness, if people were really aware and changed behavior permanently, you would get this peak and then a decline, and there would be many susceptible individuals left. It's simply that people would have changed their behavior systematically. So my point is that when you have awareness, you can get things, if it's short-term, like oscillations, to things that look like peaks, almost like Farr's law, but because of a behavior change, not because susceptible depletion. What did we actually see? In these sorts of models, and here I'm showing outputs where you can get large oscillations on the time scale where we have, here's day 75, 175, a few months later, we get another peak. In the United States, we saw large peaks that were regionally associated. They weren't all at the same time because of, there's actually an interesting relationship here to the use of air conditioning and indoor use. But you saw oscillations that went over long periods of time. So even though there was a big peak, it didn't mean that the end of the wave meant that everyone had been infected and the threat was over. It meant that we changed behavior, or people were moving outside or wearing masks. And when people reverted behavior, and in most places in the US, we saw a spring summer wave, which is what's happening here in some places, 2 waves, and then a large winter wave post-Thanksgiving, unfortunately, end of the new year, where we saw a very large wave and including large numbers of fatalities.
Professor, sorry, I have a question.
Yes.
I was wondering, I don't know, just a question. Why did you model awareness by the derivative of that and not by the density of that itself?
Right, so here I didn't show you all the models. It turns out we had one that had both the derivative and the cumulative. The cumulative is long-term awareness, and the derivative is short-term awareness. So you basically answered the question.
Okay, thanks.
So in the paper, you can see I'm trying to give you the highlights here, but we did think about both. So long-term would be D, short-term is D dot.
Okay, thanks.
Other questions? Okay.
No, yes, I have
Oh,
a
there's
few
another one. Yep,
questions.
you just have to jump in because go ahead.
Sorry. Yeah. Could you go back? I have a few questions. One of them is really quick. In the diagram you showed earlier, what was the D? Before that.
Before that.
Before
How
that.
before that?
Yes,
Yes,
that one.
this is an individual who there's a fatality. So in the
Oh, okay.
community, there's a fatality. And because of that, my point in this, I'm trying to give you, look, my training originally was in physics and I do quantitative biology. I work on viruses, but I want to try to say, we would say the essential physics, the essential mechanisms by how these things work, even without the model.
Okay. Okay.
Core idea here is when individuals have had fatalities, that awareness leads to cutting off of links rather than the links happening, but interacting with recovered individuals, which is a susceptible depletion mechanism.
Yeah.
This is an awareness mechanism. So you cut the links rather than having wasted links, if that makes sense.
Yes, it does. And then in the model you just showed us, the only way for people to leave hospitalization is by death, right?
Yeah, so there's obviously in reality, most people go, well, not most, but most people go to the hospital, recover, but we're just trying to make a simple model to add a time delay. So I'm only keeping track of the individuals who go into the hospital, who have a severe case and have a fatality. We've dealt with other models where we break up that. So some people go into the hospital, then recover. Some people go to the ICU, and of those, a fraction, maybe 50%, don't make it out. So we've built more complicated models. Here I'm just having the minimal model to just have a delay between infection and fatalities. Because if we don't have that delay, it's too quick and you get a different kind of dynamics here with the timing.
Okay. Yeah, that
You are
was one
right.
of my questions.
That's all. That just changes the timing for there. In effect, this leads to a sort of delay between infection and fatalities, which means there's a delay, and it has some of the similar effects of delays. It can cause instabilities because people are reacting to old information in some sense.
And then the awareness in this case is dependent on the number of deaths. So the more deaths, the stronger the awareness.
Correct.
Okay.
And it's either the new deaths or the cumulative. And those are the two kind of short-term and long-term awareness ideas that we played with here.
Yeah, I'm thinking if there's like, would it be possible to be a case where like awareness is so large that a large portion of susceptible individuals like change their behavior and they become less likely to be infected, but then things get better and then like this new giant portion of susceptibles is available, and like this wave doesn't dampen as much, because in the model the waves are like really dampening, and in reality like waves got bigger, not got bigger, but like they grew over time.
Yeah, you can. This is a very good point. You can see in this model, because we're applying the same time invariant awareness model, means it's a state model. It depends on the state of the disease. Then the biggest awareness we'll get was in this first peak. So we'll kick it down, but because they're having people who are infected, if the same disease unfolds going back without any waning immunity and other features, then inevitably in this model, the second peak is smaller than the first peak. But first of all, people can change behavior so that they go back to near normal levels, also with waning immunity and even evolution of strains so that future waves can have even more spread or transmissibility. It doesn't preclude a higher outcome.
Okay.
But you're right that I would have to add new features to the model that you see here to get the things on the right.
Okay.
My point here is also to say that we can get some qualitative features. What did we try to communicate about, and what were the gaps? One of the implicit themes, which I'll make explicit now based on your questions, the models weren't all right. Going back to that first thing before, which was the best science we knew at the time, and what do we still need to do? This notion of having waves and shoulders was not commonplace knowledge, that this was sort of a feature of epidemic models that could happen when you had this feedback. And yet, if you put it out there, we can get the qualitative feature, but the quantitative feature, as you said, may depend on other things. And I think
Okay.
it certainly has to do here, these timing. One of the unfortunate features of SARS-CoV-2 is that the waning immunity period around 6 months, based on both the nature of infection, something in etiology, and disease evolution, means that a whole new bunch of people will become vulnerable again,
Okay.
right?
Thank you.
Yep. So there's more left to do here. This is not the end of the story.
Hi, Joshua.
Hello.
It's Laimara. I have two questions.
Go.
One is Beckett slide 79, I think. The one.
Yeah, this is going to be impressive that there's going to be like 150. Slide 79. Yes, go ahead.
Yeah.
There we go.
No, I got the wrong one. It's the one before. Is it the? Yeah, it's that one.
Okay, ask your question. Yep.
The question is it says in the second model, the awareness one, like the second moment of the model, I don't know, that there's 8 potentially infectious contacts and 1 or less infection. But what are you calling potentially infectious contacts there?
Meaning that if you look, there are 1, 2, 3, 4, 5, 6, 7, 8 susceptible individuals. If there was a contact with those people, that could potentially lead to a new infection. That's what I mean.
No, that's not what I meant. In the first case, there were 9 potentially infectious contacts, 3 new infections. In the second case, there was 8 potentially infectious, 1 or less infection. 1 person is dead that I got, but the difference between those two cases, it seems to me, is awareness. What are you calling potentially infectious contacts? Are these contacts where people are talking one-to-one, not wearing a mask? What is that potentially infectious contact? Because because I thought awareness would diminish the number of potentially infectious contacts per se.
I understand your question. So let me try to break it down in terms of just in a world and the sort of, maybe it's the, in a world in which any interactions happen, then this infectious individual on the left, there are 9 people who they could infect. That's what I mean potentially. Like if they interacted, that could lead to an infection. That's all I'm saying. On the right, because of the fatality, there are only 8 such people. That's all I'm saying. Because of in the left, if there's not awareness, then one interacts in a certain way. Maybe these are the 3 where people weren't wearing a mask and led to an infection. So maybe this eye interacted with all of these, but of these, only 3 were without masks. On the right, because of awareness, there are fewer such risky interactions, and now we're down to 1. So when I said 8 versus 9, this is simply giving you a census of the number of people who could be infected. That's all I'm saying. The major point here is that effectively the beta, which remember is a product of the number of people you interact with and the probability of infection per context. So I can't answer your question because it's a product. Either one of those things or both could have happened. The major point on the right is that when the number of these transmission events goes down to about 1 because of changes in behavior rather than susceptible depletion, you can get a peak in incidence even if S is near N, rather than S being much less than N. If that's not clear, I'm happy to take a follow-up. That's about as clear as I can get it. I hope that is
No,
better.
it's clear now. It's clear now. It's mostly just the words that were used.
I hear
The second question is, have you done any model that included like information because it's awareness is a function of death, right? But only the number of death wasn't enough to raise awareness in some cases because of misinformation and other stuff. And not only misinformation, but also social conditions. Sometimes people were aware of the risks, but they still had no option. So were there models including this sort of stuff?
There are other models that try to look at joint dynamics of information and epidemics. So information spread, awareness spread as its own contagion process, for better or for worse, right? I don't have that in my slide deck that goes beyond what I have, but if you follow up with me, I can give you some references. But I still think that this issue of awareness and what people do with information is going to be a theme. If I get to it, I hope at the end of my talk today. And Stephen will also, and I cut short, Stephen, a few of the things with Ali, hoping that you are going to go over that. Is that right?
Well, yes. I will, yes.
Yeah. So Stephen is actually going to go through some of our efforts to evaluate how people perceive information and what kind of misestimation they may have and how we might correct that misestimation to change behavior. That is hard, right? It's just hard. I don't have a complete answer for you. We've made steps. I'll give you a prelude to that, and Stephen will dive more into at least our take on some of it. Sound good? I assume that's
yes,
okay.
Thanks.
Okay. Where was it? Yes. So let me just keep moving ahead for a little bit more. I think I will probably be mostly on slide deck today, but I will try to jump in with a few mathematical notes, as it were. And you'll obviously get to play with some of these core models in the laboratories to come. But the other feature of these epidemic outbreaks is that if there's just short-term awareness, what you end up getting generically, unlike Farr's law, unlike the IHME model, if most of what is changing our risk of infection is our behavior rather than the depletion of susceptibles, then the generic output is not a big peak and then it goes away and we're done. It's a plateau or a shoulder. And what you can see here in this particular model is what these kind of models do, right? If there's short-term awareness, where you end up sitting for a very long time near kind of the same level of infections. And you also get an asymmetry. You get exactly what Farr's law says you shouldn't get. China is a bit of an exception. They also imposed a society-wide lockdown, but as we know, there has been a major epidemic wave in China, the magnitude of which is very hard to estimate. Here's Iran, Italy, UK, USA. You should notice there's this, and there's something that looks like this, right? There's a fast ramp up and then a long period of stasis. If this were symmetric, it would have been done by May, right? It should have been done by around here, but it wasn't. There are levels at which it seemed to stay nearly constant for a long time, and these are state level views, 50 states, and all the levels of granularity differ. I think it's obvious that there was a rapid increase and then in most places, this long plateau. One of the first things that I tried to do when I communicated was warn about the risk of a long plateau. And with Stephen leading the charge on a Georgia level effort, we did the same of showing how these kind of models, whether it's through spatial spread or through awareness, could lead to this period in which it doesn't just go up and go down, but stays because most people were immunologically naive. But as scientists engaging in public health, we get this feature and we have a model and it looks like it's right. But are we right for the right reasons? And so we began to probe this a bit further. I hope everyone is here is clear. This is the daily number of reported deaths, y-axis, time. It's basically April, May, June on the x-axis. You should take away that things look like plateaus or shoulders. We have a mechanism. We think that there's a sort of relationship between mobility and fatalities. So how would we test that? We decided to look at what are called these Google mobility indices, and there's different ways of doing it, and I haven't unpacked all the details here. But this is, in essence, a proxy on the x-axis for the extent to which people are going to work and retail stores and shops, to lower mobility or mobility associated with staying at home and then doing your essential grocery trips. If you look at the data in the early part of the pandemic, and it differed based on socioeconomic levels, ability, as you point out, to quarantine or isolated home, depending on work and type of work, simply couldn't be possible for many people. Many people who were more vulnerable either socioeconomically or because of the density of how they live and so on. It wasn't possible to change mobility. At a population level in the US, one saw a big signal overall from higher to lower mobility, and then a return. That's also a political issue, an economic issue, and I can't get to the bottom of all that. But obviously, if one makes a policy change that says stay at home, and there's not the economic plan to make it feasible to stay at home, people can't stay at home. They have to keep paying bills, and you have to keep going out to work to pay those bills. What we expected to see was that there should be high levels of mobility with low levels of fatality at the start of COVID. And as COVID deaths go up, and I'll sort of write what we thought was going to happen, we thought the trajectory should look like this. Starting here, deaths increasing, leading to lower mobility. And as the lower mobility happens, then we would get lower number of fatalities, and maybe eventually we'd get this return, and this sort of counterclockwise cycle could repeat. Does everyone understand that? I want to highlight that there was one state in America that seemed to do that, Washington. Went to the left, deaths started to go down, there was some increase, it did this counterclockwise move. New York went back in on itself, and some of our models says it should kind of go back in on itself. But almost every other state had the opposite signature, where mobility was going down as deaths were going up, but even as deaths were going up, mobility was increasing. Do you see what I'm showing you here? Which says that although it seemed like the pandemic was getting worse in terms of severity, there was actually an increase in mobility and could lead both mobility, so people were going back out into retail, and there were these fatalities going on. This led us to lead to some changes in the model, which I can't go through all the details, but this is what we initially thought might happen. That if there was no long-term awareness, we would have this behavior like mobility go down, deaths go up, and we kind of go back and forth, a bit like New York. That there would be this peak and it would decline, and we'd kind of stay almost on the same line. And if long-term awareness, we would go down here and we could get the crash of an epidemic with low mobility, because people would remember how bad it was and wouldn't go back to the prior levels of mobility. Another version is that we get this decrease, and then there's something like fatigue, where people, either because they were tired of staying at home or could not stay at home, so it's not meant to be a sort of, has the negative valence, it's just meaning that people had to go back out, then deaths per day increase as mobility increased. Another version, though, and this could lead to very high epidemic outbreaks, you see it gets much higher. In this story, there's a fatigue element, it's going up, but the deaths never go high because there's some change in behavior, like mask wearing. So on the mobility reports, you would see an increase in mobility, but deaths wouldn't go up because people would have substituted some behavior. So here we have a pure awareness model, which doesn't seem to apply to most of our states. Some severe outcome where there's only a single peak and then recovery, and one in which there seems to be intermediate cases. So we believe what happened here in the US, at least, and in many places, is that there was this reaction due to awareness, and then a fatigue element, but there was substitution, as we know, mask wearing and other changes that led to at least less worse outcomes than could have been. If you look at adherence to protective behaviors, what you often see is that there was a period in which there was a percentage change spent in residential locations. And here is retail and recreation visits. There was some period in which people began to go back out later on. So people did end up having these changes, and they differ by region, they differ by socioeconomic level. So there's certainly evidence, and also trust in government, there's certainly evidence that there has been pandemic fatigue, and it's also just not sustainable for that long period of time, given socioeconomic levels and support for people's ability to stay at home. It's not possible, as we've seen on long time scales. This is an ongoing research effort. But there's still one more piece of the puzzle that I wanted to explain. And so I'm going to switch gears a little bit here. I don't know if there's questions yet, but I did want to switch gears. Yes.
Yes. We have question.
Yes, I have a question that I guess you're about to answer it, but I'm going to make it anyway. In the previous model, the awareness model, that I was thinking if there could be a term about, because we have a new term for susceptibles changing their behavior with increased awareness, right? I was thinking, in the case of infected people, could a term be added to change their behavior? So, for instance, I know I'm infected, and then I change my behavior.
I'm about to do that.
Yeah, but I was going to ask, sorry, doesn't this somehow translate to the term that we already added in the susceptibles? Because I guess the changing behavior from infected people would have an effect on beta, right? So do you see my question? I don't know if I'm being clear.
I think I do, meaning that you're going to have different behaviors depending on your infectious state. But there's a problem with that, which is that not everyone knows they're infected. So let me suggest some way to deal with that. And I've dealt with it only partially here. So I'm giving you different slices of what could happen. But I want to raise this point that in the prior model, everyone sort of behaved the same way. But that's not how everyone behaved. And so in this next section, I'm going to talk about ways in which I'm going to create a dichotomy, which of course there's a continuum, but I'm going to create a dichotomy between people who feel one way but are infectious and may behave differently versus those who definitely know they're infectious and behave a different way.
Yes.
If that makes sense.
Yes, okay.
So I'll try that in a moment.
Okay, thank you.
Are there other questions here? Is there another one? I can't tell.
One more.
Is that yes?
Yes, I do have a question. If you could change to the previous slide, please. One thing that I was asking myself while looking at this graph, that except for New York and Washington, they were the only cities that followed the pattern you expected.
States, yes.
I was thinking, do you think there is some sort of relevance if the city is like very big and with a big population or smaller? Do you think there could be some sort of influence in how this curves behaves itself?
So it's hard to know. New York is a very particular case, unfortunately, in America because of the intensity at which it hit New York, perhaps harder than any other city in the United States. And there was such an intense wave, and people didn't just change behavior. Many people just fled the city if they could. And many people couldn't. And it really did transform the way people behaved. And as you can see, it went up and then went back down. It wasn't like people went up and increased behavior. There was a dramatic change. And that was in New York City. And that was really, in that particular case, such a disproportionate impact on the state level outcomes. I agree that one is its own category. Washington is an interesting case because at the University of Washington, and the governor, because they had one of the first introductions, they were one of the most aggressive in terms of being first to impose, whether it's lockdowns, awareness of canceling events. My impression is that they just simply did a different job at the state level. Seattle isn't necessarily a disproportionately sized city in a state. Georgia, for example, we have about 10 million people. Atlanta makes up a very large fraction of that, right? And yet you see here, we went through this large period of a plateau, very different than the Washington case, right? And Los Angeles, California has major cities. I mean, there's not, Massachusetts has Boston, which is a major city and went through a long plateau. So it's not clear to me that it's that simple. COVID was a societal transforming event. So, you're looking rightly for patterns, but it tends to be more complicated. I think the generic pattern, though, here of this clockwise rather than counterclockwise motion is something generic, and it's something important that we need to still try to figure out.
I see. Thank you very much.
One more question.
Okay. I only have 100 slides left.
Can you go back to the graphs?
I have only 100. I only have 101 now.
Okay, so we see that when these plateaus happen, mobility is increasing again. We don't see the number of deaths go up again. So you think the vaccination processes in this graph is near the peaks there?
Yes. So this is the part when we were making hypotheses. You'll notice that in our initial model, in which we just had short-term awareness without long-term awareness, and there was some kind of fatigue, we get it going up. But you rightly point out that it seems to go horizontal. I think that's your point.
Yeah.
So that is kind of one of the reasons we put together this last model, which is there was some substitution. We speculate that's because people started to go back out, but we're wearing masks. And I don't have my mask wearing CDC survey data, but it went from low percentages. And then in March to about, maybe it was in the 20% to 75%. So there was a substitution so that people were going out and wearing a mask, at least temporarily in the US, and that led to changes in risk. So we think that there were substitutions going on that made it possible for mobility to go up, but not leading to these large increase in cases and therefore fatalities.
Yeah, thank you.
Okay, but let me go and unpack it, because not everyone felt the same way and not everyone behaved the same way. I've used this figure just from MedPage today simply because you can see this individual feels fine, but in their breath, there are going to be infectious viral particles that can reach others. And especially if they feel fine, there is a higher chance that they interact more frequently and don't wear a mask and don't stay at home, because there shouldn't be any reason for them to stay at home. Either they have a mild case, so mild they would probably ignore it, or they're pre-symptomatic and have no awareness that they're infected. And just as a personal anecdote, in late 21, in my family, all of us became infected, first of which was one of my children who felt fine. They were going to go to some outdoor birthday party. The birthday party's host wanted everyone to get tested. At least the parents, my wife and I had already been vaccinated. My children weren't yet eligible in the place where we were. And we went to get a quick antigen test, and it came back positive. The child felt totally fine. And I'm sure we had always been exposed, and we were all infected within a couple days. So when you feel fine, you're out and about, and you don't have awareness, you're more likely to infect others. So you may raise the question, well, how important or relevant is any of this? It turns out that when looking at asymptomatic and symptomatic CT values, and I'm not going to go through all the details, this has to do with how many cycles on a PCR based test you need before you recognize that you detect a signal. And lower CT values means more infectious or more viral RNA and therefore DNA that comes out of the machine. So therefore, these low values sit at the top. These are the symptomatic individuals. These are the asymptomatic individuals. And although there may be a longer average of having higher levels, as you can see here, the individual point levels are quite comparable, right? So there's a slightly higher peak that lasts a little bit longer, but you can see that they're still, even if you're asymptomatic, have high periods, and even in some cases higher than that of the symptomatic individuals. Asymptomatic infections happen quite frequently, and they can lead to transmission. If one looks at the fraction of subclinical, because asymptomatic is kind of a challenging term. Maybe I felt the slightest bit of sniffles, or maybe if one took a temperature, it would be slightly off, but these are all subclinical. A doctor wouldn't be able to identify that necessarily as SARS-CoV-2. And as a population average, it's almost 50-50 that infections are subclinical. And amongst young, largely healthy people like you all, it's actually disproportionately the case that you may have a mild or asymptomatic case. What does this mean? Is this good or bad news to have all this asymptomatic spread? For the individual, it seems good. My claim is that for the population as a whole, asymptomatic transmission actually makes things worse in terms of severity. So I will make a schematic of this idea. You can imagine that we have on the x-axis the fraction asymptomatic. So the fraction of cases that have no symptoms. From 0, everyone has symptoms on the left, to 1, everyone is asymptomatic. And I'm going to assume if you're asymptomatic, there will not be a fatality. So this is going to go per case level. The fatalities are going to go down to 0, whereas when everyone is symptomatic, there's some case fatality rate, which is over here, which is higher. However, the number of cases has the opposite relationship. When everyone is symptomatic, now to answer your question, I'm going to assume that symptomatic individuals recognize their symptoms and reduce their interactions, leading to fewer cases, fewer infections. Whereas if everyone is asymptomatic, they go about as normal, don't change behavior, you would have more infections and therefore more cases. What this is starting to imply at the population level is that the severity that we worry about is the cumulative fatalities at the population, which is a product of the number of cases times the fatalities per case. Where do you think this is going to peak? In the middle. For things like Ebola, which has a very high fatality rate on the order of 50 to 60%, it can be dropped a little bit, but not much when there's care available. But there's very little evidence of asymptomatic transmission or spread. It's very bad for the individual, but at the population level, it's not infecting nearly as many people. And therefore, the outbreak sizes, 2014, 15, West Africa excluded, are often quite small. And even that one led to on the order of 10 to 20,000 fatalities, not on the order of many, many millions globally. So strangely enough, this asymptomatic transmission, which seems good because we have cases that don't lead to bad outcomes, can actually lead to worse outcomes at the population. So now let me turn this into a model. We have susceptible individuals, exposed individuals, and now with some probability P, I'm going to classify an infection as asymptomatic and 1 minus P classified as symptomatic. And you could imagine I write down the system of equations, which I don't even need to do at present. Amongst the symptomatic individuals, a fraction will lead to fatalities, a small fraction, maybe on the order of 1%. and the rest will lead to recovery, whereas all the asymptomatic people will recover. And the only other twist, I just mentioned the fatality rate, will be that there will be a reduction due to symptoms-induced isolation of delta. And I'm going to assume, sorry I used delta in another meeting before. Here I'm just talking about the reduction in the interactions by a certain factor. Okay? So you can already imagine what might happen here. We might think of what is our R effective. And this is going to be something like the R naught for asymptomatic, right? Times P, the fraction that are asymptomatic, plus R naught symptomatic, because maybe the symptomatic people are slightly more infectious and will cause slightly more infections, times 1 minus P, right? We just add this up. But this is going to be reduced by delta, so we're going to get a 1 minus delta term here. Okay? What you can begin to see is with delta gets very high. Imagine delta.
Oh yeah, are you listening? Let's see. Okay.
A fraction 1 minus P that could have this outcome. So you could see that this value, which tells us about strength, is going to tell us something about the size of the outbreak. Because remember, the herd immunity threshold, HIT, is something like 1 minus 1 over R naught. Right? Remember, when R naught is 3, 1 over 3, we get 2/3. Do you remember that from before? Right? So if all of it is coming from this
Hi, Joshua.
asymptomatic route, we're going to get something like R naught minus 1 over R naught people infected, which is the same as saying this R naught A times P, because that's the fraction that's asymptomatic, minus 1, over R naught A P, and then this whole thing, which is the fraction of people who've been infected before the disease goes down, of those people infected, 1 minus P will be symptomatic times 0.01, because that's my fatality rate, or F, right? This is my F for fatality rate. This will be population fatalities. Pop fatalities.
Hey Joshua, we lost you for a second with Wi-Fi and we
Oh no.
missed a lot of this equation derivation.
Oh, okay. Can I redo it? Do you see it at least?
We see it.
Good. Where did you lose me? At which point on the left?
The first line, RF, R naught P plus R naught.
Okay.
Yeah.
Okay, let me just start over left to right, if that's easier. Is that okay? People recall from this lecture that I've said the herd immunity threshold is just 1 minus 1 over R naught. I see a thumbs up there. That's right. You remember that. So when R naught is 3, we have only 1 in 3 people are going to be infected, right, amongst that group, and we kind of get replacement. So we need to get 1 minus 1 over 3, which is 2/3. And if R naught is 4, we get 1 minus 1 over 4, which is 3/4. So it goes up and up and up as R naught goes up and up and up. That's good. This is just an equivalence. I just moved R naught to the top. I got R naught minus 1 over R naught. So again, it's 3 minus 2 over 3, 2/3, 4 minus 1 over 4, 3/4, 5 minus 1 over 5, 0.8, and so on. Is everyone with me? If I assume that symptomatic people isolate, so delta is 1, then the spread is always through the asymptomatic people. I know that's not true, but I want to give you intuition here. If that's true, then I can take this R0 and just take R0 A, the asymptomatic reproduction number, times P, because only a fraction, and I'm just replacing that. That's all I've done here. This is assuming delta is 1. So this is the herd immunity threshold. This is how many people would be infected if only asymptomatic people are transmitting. This is, though, the number of people who have been infected. Even though only asymptomatic people are transmitting, a fraction of people of those had been symptomatic. That's 1 minus P. And amongst those symptomatic people, a fraction died. So if I take the herd immunity threshold times the fraction symptomatic times the individual fatality rate, I get the population fatality rate. Okay? And then you could ask the question, where does this peak? And it turns out that this formula, although it's not the true value of the outbreak size, doesn't peak near P equals 1, because you can see when P equals 1, this is going to go to 0, right? Nor is it going to peak when P equals 0, because there's a minimum threshold. This thing here needs a critical value of P in order even to take off. So we have zeros on either side. So just this little formula shows you why there should be a peak in the middle. That's my point. Are there questions about that? This is one of my few derivations here today. Steve, did that come through?
That all came through, and no questions right now, but it might just be sinking in.
Yes, that's fine. So let me move ahead. So that was this formula. Oh, wow, it didn't actually, I thought it was going to erase everything I just wrote. It actually remembered what I wrote. So this is this little intuition for what this model could do. Of course, there are many ways to move these things up and down. And I just want to recognize the case that with vaccines, some of what we're doing is stopping infection. But really, the point of vaccines was to move people who were infected from being symptomatic to asymptomatic or mild to reduce severe infections. The vaccine efficacy was measured in terms of reducing severity. That's what it got. All of those mRNA vaccines in the US and the other vaccines were tested on their ability to reduce severe disease. So these vaccines are moving things from this category of outcome to this category of outcome. Yes.
Why wouldn't vaccines work as a mechanism to change the distribution of susceptibility in a population instead of
that was the hope for sterilizing immunity, that you would just be totally blocked from being infected. That
Yes.
turned out not to be the case. That would be great. People are trying to do it. That is just not how things work. So they were the objective metric for example, if you look at the early Pfizer vaccine paper in New England Journal of Medicine, you'll see that the two arms, which were the people who got the placebo and the people who got the mRNA vaccine, the evaluation of whether or not it was working was not through subclinical infection, but through symptomatic infection or severe outcomes. So the ability to stop hospitalization, severe outcome, disease, and fatalities.
Okay, so for this case, they didn't change anything about the
It did.
distribution.
I don't want you to think
Oh,
it
okay,
also
okay.
reduced. It did both, but it was evaluated on this metric.
Okay. Thank you.
The hope was that it would just reduce everything, like no more infections, but that turned out not to be the case, especially with evolution of strains and then people who had been vaccinated or even infected with the original strain could be infected by Delta or Omicron, so there was both waning and also strain evolution.
Okay.
They were evaluated in this sense, but they had both consequences, just not perfect.
Thank you.
Okay. Other questions?
No more questions right now.
Okay, let me just keep going through it. So I gave this derivation, and I hope you can see that when P equals 1, we don't expect any fatalities. When P, and there's a critical point here, when P is less than 1 over R naught of A, we also don't expect any fatalities, because if it's only going through the asymptomatic route, then depending on how many people are asymptomatic, we have to have enough asymptomatic in order even there for the disease to spread. So we get zeros on either side, and it must peak in the middle. Okay, so already in this little equation, before I don't even have to do much more math or do crazy final size predictions. We already get this kind of answer. Okay? What actually happens then when we build a model? So we take this idea where there's delta, and I have 3 panels here. Fraction asymptomatic. The panels correspond to R naught of 2, 3, and 4. The curves denote different levels of behavior change by symptomatic people. From total isolation, as soon as they get symptoms, they isolate, and there's no pre-symptomatic transmission in the dark, to the gray, meaning a little bit less, about 60%. What I hope you can see that in each one of these cases, although as we increase the strength, the disease gets worse in terms of the severity at the population level, the size gets worse. The peak size is always in the middle, somewhere between 20 to 75%. And right now, the estimate for SARS-CoV-2 is about R0.3 and about a 50% asymptomatic fraction, and it's somewhere where people aren't perfectly reducing. Our point here is that the asymptomatic transmission is truly a double-edged sword. Good for the individual, but potentially worse for the population as a whole. That is not something that I think is still widely understood, because it leads to all sorts of downstream consequences. These numbers are not the herd immunity threshold. This is a consequence of running this epidemic model out all the way to the end and just seeing what the total fatality rate was. It doesn't include vaccination. It doesn't include waning immunity. It doesn't include a lot of bells and whistles that might otherwise happen, or things like awareness, which would lead to multiple waves. Yes, are there already questions now that I got through this idea? I'd like to get through one more idea if I can before, and then I'll take questions. Is that okay?
That's good.
So we did consider what would happen with some sort of either vaccine or a second wave or a type in which some proportion of the population had already been infected, has some immunity. And it tries to address this question of, if Omicron is less severe, why could COVID-19's deaths rise? Why are mild variants worse at population levels? And the reason has altogether to do with transmission. In this example, it's the same sort of model as before, but we add a prior wave and then we restart with another wave, which has different fractions of P. So you can imagine here was our wild type. And then the next one comes where we have the same level of asymptomatic or a much higher level of asymptomatic spread. And depending upon what the asymptomatic level is, here are the prevalence of cases and daily deaths in these 2 variant cases. Here's the first wave. And now, in fact, in these new models, going back to the point before, depending on how much cross-in protection there can be, you can get a larger wave in terms of the peak daily deaths can go up, even if the variant is milder, because it infects so many more people because people are not taking protective steps because they're largely asymptomatic. So you get these huge peaks in prevalence and a larger, although narrower, peak in daily deaths, even if at the end of the day that other wave has a wider fatality rate and leads to more fatalities. You can get transient waves of intense fatalities in a milder variant. This was one of the things we were trying to explain in terms of the dangers of asymptomatic transmission in this model. And I just want to finish this section with this idea. If we want to take action to protect communities and build pandemic instruments, for SARS-CoV-2, and in my view, the worst thing for pandemics to come is a risk of asymptomatic transmission and substantive fatality. SARS-1 did not have this pre-symptomatic or asymptomatic transmission route by and large. SARS-CoV-2 did. Even though it had a lower fatality rate, the fact that it could reach many more people was really the key unfortunate ingredient that led to so many more people being infected, and therefore a small fraction of a much larger number having severe, if not fatal outcomes. And if we know that asymptomatic transmission is the big deal, then our messaging can't involve just scanning people as we used to do with temperature sensors, because they could feel fine and transmit. We have to do things, whether it's through masking in a high impact way, or doing better with indoor air, just like we do better with indoor water, and we try to filter it in advance, no matter what anyone does. And also talk about how these risks of asymptomatic transmission are not the same with different ages. They vary, right, across ages. So people's experiences can be very different. If people don't understand the rationale, it's hard to build public support for action taken. And that's where I want to pause. I have a whole nother section at the end, which I'll get through some, but I'm happy to take questions about this model, which I think is a quite important and underexplored feature of COVID. So I'll pause here. Other questions? I can't tell, Stephen, if there are any.
Yes, one question we have at the back.
Go ahead.
Okay, everything is still sinking in, so I'm not sure if I can properly phrase this question, but could you go back to the previous slide just for a bit?
This one?
Yes. I think the first thing I can ask is for you to maybe explain a bit again about how the Plato of these curves actually is always in the middle. I didn't understand very well why.
Okay. So I think you mean the peak. Why is the peak cumulative fatality in these models in the middle rather than on the edges, for example, right? Let me distinguish the individual level severity from the population level severity. The y-axis is in some sense the population level severity, the fatalities per 100,000 individuals. In a disease for which if everyone had been infected, and here I'm using a 1% fatality rate, and everyone had a symptomatic case, there would be 1,000 fatalities per 100,000 individuals. Okay? But remember that the asymptomatic transmission, the asymptomatic fraction of incidence is P. So when P is 1, everyone has an asymptomatic case. We will have no fatalities. When P is 0, then everyone has a symptomatic case, and technically we could get up to 1,000 fatalities per 100,000 individuals. But we don't. And we don't because, first of all, not everyone is infected. Even if R0 was 4 and no one changed behavior, but they are changing behavior. And the way I've modeled behavior change is I've assumed that symptomatic people change behavior and asymptomatic people do not. And because of that, let's go down to this case here at the bottom and focus on the black lines. Delta is 1. No matter what R0 is, you'll see that when delta is 1, we need a critical level of asymptomatic infections in order for there to be a substantive number of fatalities at the population scale. Why? Because if it's too low, then what ends up happening is that the people who are infected symptomatically, they don't infect anyone else, and then a very small fraction of time they might die, 1%, but they don't infect anyone else. So effectively, the population scale looks like a 0. You'll notice this number, R0.4, when there's no symptomatic transmission, this little increase starts at 0.25. For R0.3, it starts at 0.33. For 2, it starts at 0.5. So this is literally the herd immunity. This is the unstable point of this equilibrium, which I'm sure you did with Roberto, because this is the only way for the disease to transmit, right, is through that asymptomatic route. And so if I go back and remember, if I draw my thing again, where I have, what? Nope, I need my pen. If I have to have R naught A times P, this must be greater than 1 for the disease to take off, which means P must be greater than 1 over R naught A. This is why all these black lines start at 1 over the R naught value. Okay? So on the left-hand side, everyone is symptomatic, but there are not people being infected. On the right-hand side, there are tons of people being infected, but none of them are dying. That's why the left and right-hand side are 0, and in the middle, it peaks. Does that make sense? Or does that help you?
Yes, it helps. Thank you.
This is this little result when delta is 1, but when delta is not 1, you get a more complicated expression, and it keeps moving to the left in terms of the critical amount of asymptomatic spread that would lead to large-scale transmission. And when R naught is 4, any level would do it, right? Because if people are not taking protective measures and it's such a strongly spreading disease, you're still going to get outcomes. And just to point out, when delta gets too low, then the peak does go to the left. So the peak is at P equals 0 when people don't take protective measures. So when delta gets to be below 0.5 and the R naught equals 4 case around that much, then the peak value of fatalities at the population level is when everyone has a symptomatic outcome. But when people take protective measures, you get this intermediate level effect, which I think is a very plausible kind of modeling scenario to consider. Other questions? Stephen, I'm not hearing any, so maybe I should get to the last section.
Yes, let's move into the last section.
Okay. And I'm not even doing the big math today, but you're going to have a chance just to kind of give folks a preview. Stephen, when is you have 2 more? Do you have one or 2 more left?
There's 2 labs, and then I'll give a talk on Thursday about some of the other models that we've worked on.
Okay, great. So I'll just do a little bit of a preview here in the last 15 minutes. We'll get as far as we get, but I'll just do a preview of some of the things that we did. Summing up, how are epidemics supposed to unfold? People infect other people until their susceptibles depleting and it goes away. Why has it been so difficult? Because that's not quite how epidemics work. There's often heterogeneity, so people are infecting different numbers of people. And also because there's asymptomatic transmission and awareness, which means that there can be peaks that go up and down, not because we've run out of susceptibles, because people have changed behavior, and some of that behavior change has a lot to do with asymptomatic and symptomatic transmission. So I'll try to get into, in this last section, some of the practical steps. This is the context that we have in mind when we're trying to build models to deal with COVID and also prevent future pandemics. We didn't get into the forecasting business. There's a wonderful paper by Susanna Manrubia on why forecasting is fundamentally hard, because these are exponential processes and you're trying to fit data that has some slight difference, and you therefore have your error magnified exponentially. We tried to do something different. If we are concerned about super spreading, then we need to build models to communicate to people that maybe there's a risk of transmission in large events. If we think asymptomatic transmission is an issue, then maybe we should build testing programs to intervene even if people have no symptoms and isolate them so that we have less transmission. These are the kind of ways that we took steps in my group, working with partners, broadly speaking, to use models productively and not just make predictions or forecasts, right? To actually take active steps. And that's been our priority since early 2020 and continues to be our priority moving forward. So I'll just give you a few examples. We'll go through these, maybe in a little bit faster time scale, give you a taste, and I think Stephen will talk about this one at length. One of the things that we worried about, as I explained, was this risk of super spreading, which was evident from the very beginning, particularly in indoor environments because of the airborne spread, and also because there's a large number of people that could interact with. So what we tried to do is develop something which would let people know at some level their risk that they may be exposed and allow them to take steps like not attending the large event or meeting outdoors or increasing ventilation or wearing a mask. Stephen will get into a lot of the details, but we developed this thing called the COVID-19 Risk Assessment Dashboard, and this was released in July 2020. And since its release, largely in the first year and a half, we had more than 16 million visitors, delivered 60 million plus estimates. It involved a very large team, of which Stephen was key, especially in the development of our international components and our mitigation and intervention experiments. The principle of this code and communication tool is the following. A, there's asymptomatic spread, and B, because of limitations in testing, there's an iceberg-like effect. We see a fraction of the cases, and icebergs, well, majority of the mass, somewhere between 5 to 10 of the mass of the iceberg is below the surface. That's more or less what happened with COVID. That there were many more actual cases than reported cases. And because there were many more reported cases, unreported cases than actual cases, it meant that even early on in March 10, this is a tweet and I won't explain all the crazy details here, but I was trying to communicate the fact that at events of different sizes on this x-axis, from dinner party back to March Madness, depending on how many actual infections there were in the US, which I believe to be more like on the order of thousands, even though there were only hundreds being reported, there was a very large chance, which are these isoclines, that someone in that crowd might be infected, which meant there was a huge risk that there could be onward spread. And we knew this very early. It turned out by the end of December 2020, we had 16 million or so reported cases, but the CDC, using a couple estimates by mostly serological surveys, but also backcasting the number of infections that could have been responsible for the number of fatalities, that there probably were 80 million infections. So something like a 5-to-1 ratio. It turned out later on to be closer to 4 or 4.5 to 1. This meant that the documented cases being reported on public health sites was not an accurate representation of risk. You had to increase that number substantially to get a sense of how many people might be infected, and also recognize that it was local. So how do we translate this into something personal and relevant? Our idea was to imagine that you were in a crowd, a small crowd, for example, in which case if we knew the probability that you might be infected, maybe no one in that group would be infected. But if you had a larger group, there's a higher chance that there might be one infected individual. And because of the nature of airborne spread interactions, then there's a chance there could be a super spreading or large event. And just to make the point here, if P is the probability that someone is infected in the local population, 1 minus P is the probability they're not infected. And if there's an event of size N, 1 minus P to the N is the probability that no one in a group of size N is infected. And therefore, 1 minus P to the N is the probability that one or more individuals is infected in a group of size N. Made sense? If we have to estimate P, how do we do it? This is the prevalence. We can't use cases as the good indicator of prevalence. We had to take the recent cases, so the number of new cases over the past 7 days or so, or 10 days, we believe those people are still infectious, and multiply that by this ascertainment bias, and then we get a per capita level, our estimate of prevalence. And that's all we did. That's what we did. We took county level case reports, accounted for ascertainment bias, and were able to give an indication at a particular location that in one or more in a group of a certain size, which allowed this slider, and Stephen will explain all this works, you could change event size and the map would recast itself and you would get a sense of how many people might be infected internally, and we would translate that to a risk level. What's the chance that one or more individuals might be infected if you went to an event of that size? You can see that these risks are totally heterogeneous, right? There can be regions that have very high risk at a certain moment of time and others have relatively lower risk. We ended up releasing the resource and the paper, and then another issue came into fore, which was communication. LA Times, Washington Post, New York Times, hundreds, literally hundreds upon hundreds of newspaper articles and local newscasts wanted to think about and communicate, right, especially before Thanksgiving, but also in July during the summer wave, what was the risk that these gatherings could lead to new transmission? This became another issue. I think I'm more or less in the same position, except I'm wearing a sweater. And it's been backcast. It's the same place, sitting in my office, talking to people. Collaborator Cleo Andrus, who did the GIS visualization. She was our GIS lead. There's Stephen on Fox 35 Orlando, a collaborator from Stanford. We all tried to communicate to the public as much as we could what the tool meant, what it didn't do. And so the communication part was absolutely essential and took time. The other feature was behind the scenes. You have to have the ability to produce these estimates daily. And on some days, 500,000 people came to our website. This is well beyond, as you know, in academia, if you get 50 or 100 citations, if you get 500 or 1,000 readers, that's a tremendous level of impact. In order to communicate to this many people, you have to really hone your communication on the front end, and on the back end, make sure that the tools are working. And that was only possible, and Stephen will get in through a lot of these details, through the work of Arun Chande, who is our front end developer, Troy Hilly did the back end, Sohail Lee, who did all the work on the GIS on the front end. This also meant that we were spending a lot of time communicating. This is one particular day, there was a surge period. These are all the interviews we did collectively as a group in a single day, in terms of either we did the interview, provided information, and all of these different places had a local news report, which meant we had to have talking points and frequently ask questions and provide image and video. So all of this became a new problem. And Stephen, I hope I'm not stealing too much of your thunder. This is my last slide on it. We then also had to see what was the impact of all these interventions. By asking people, how did they change behavior? And I'll just give a preview for, I assume, some of what Stephen's going to do, to say that people were willing to change their willingness to go out to big events, but not small events. And we have a lot more evidence of how this can work, but I'll let Stephen explain that in his talk. So the take home here is that knowing something about asymptomatic transmission drove me and Cleo to work together, and then with Stephen and many others, to build real-time tools that could raise awareness, and now we're trying to measure the impact of that awareness on people's behavior. That's one example. I have one more example, but I may be almost out of time. Should I pause for questions here? Or should I just give you one more example?
Go for the example.
Okay. People are too exhausted anyway to ask any more questions. The other thing I want to point is, what can we do to stop asymptomatic transmission? Obviously, mask wearing helps. If you're wearing a mask, even if you don't know about it, you're reducing release of viral particles, especially high-quality masks. You can also do better with ventilation. Another thing you can do is test. Because if you test individuals irrespective of their symptoms, you can identify people early and potentially stop people before they start infecting others. I'm not going to push whether it's PCR antigens test, but we had PCR available to us in summer 2020, and we were able to do this at scale at Georgia Tech. And there's a simple principle, but antigen tests are also very good. We knew they were going to come down the line, but we went with a PCR-based test like many American universities. There are some negatives to them. You can catch people late, and if isolating people are probably not infectious, but if you do it at scale, you tend to catch people early. And this is the principle. If you have an SEIR model and you get exposed and then you incubate, you're infectious, you can remove people, and in your age group, almost everyone, the vast majority of people are going to have non-fatal outcomes. So eventually folks will recover, or you can remove them from the pool of interaction through testing. So the model now has this incoming incubation route and 2 ways out. And because there are 2 ways out, the reduction in infectiousness is just the rate of leaving via testing divided by the sum of rates. And what that says is that the testing rate matters as well as sensitivity, but it's really the testing. And so the one thing we fought was a battle to require masks in the classrooms. First, the state didn't want to require them, and then we won that battle, so we knew that we had some protection from masks. And so we built a model in which we have some reduction in baseline R0 from 3 down to something we thought was between 1 and 2. And what we wanted to do is test everyone, or as many people as possible, on the order of 1 week. And in doing so, these are our simulated outcomes for what we thought the number of cases might be in a school of having about 15,000 students with 90% sensitive tests. And what you can see is that even if you have an R0 of about 2, we're expecting 5,000 or more, if there's no test, up to almost 6,000 or 7,000 cases, down to hundreds. So you get quickly down by a factor of 2, and tests can reduce you even further. We're hoping to be in this zone where we have the order of hundreds rather than thousands of cases. And what we ended up building was a simple saliva-based test that took about 2 minutes to sample. People donated their saliva sample, put it into a little test tube. That test tube would get sent out to a CLIA facility, and we would end up testing this and letting people know largely in about a 24-hour period. I'll skip this other thing and just give you the example outcome, the outcome, which is that we have this percent positivity. This is August 2020. People came back. We had a surge, but we knew where the cases were. And although there was some doubt in the community that we could control it, we ended up having controlled the outbreak, except for one post-Halloween high incidence level, to less than 1%. In contrast, another university in our same state, more or less the same epidemic status, had 9% positivity and 4% positivity across the term using a community-wide but non-scaled intervention test. And the other thing I want to point out here is that heterogeneity was typical. So in order to controlling this asymptomatic transmission, the majority of cases we found were through the asymptomatic testing. There were locations which were disproportionately represented, as we expected, through SARS-CoV-2, which was good and bad. It was bad because local dorms could have very high outbreaks, but we knew where the dorms were and we could isolate them and move quickly. And just to point out that we ended up using this as a gateway to the spring, where basically, although there was an initial outbreak, the vast majority of time we were less than 1% positivity. And this was the gateway then for vaccinations that took place in late spring 2021. So I think I'll wrap up there with that second example and stop sharing, because I think I'm at the end of time. And just to say that these models became a guide, not for predictions in our case, or forecasts, but really a guide for action taking. And I hope that can be the takeaway point you can leave with when you're building these simple models. They're the start of something, not the end of something. That's all I had today. It was a lot. I even cut some short, but hopefully we got through a lot of questions. The next couple days, you're going to get through 2 epidemic lab modules, and then Stephen will explain more of the insides of what we really did and how we build these models in practice. So thank you very much for your attention. I think we probably close out. I think I'm on an infinite loop of me's on the other window. I don't know how to stop that. I'm happy to take one or two questions, but I think you're at time. You need a break and probably have either lunch or something else coming up.
Wonderful. Thank you, Joshua. Let's all give Joshua a hand. And are there any questions?
Yeah, and also obviously you, Stephen, you have, Stephen knows my email. I think all of you have my email. I will generate a PDF copy of this, and Stephen, I'll share with you to post on whatever the Slack or however the channel is. So I'll post it onto our shared drive, and if you could share it with Flavia, etc., that would be great. So everyone could review the slides at their own leisure.
I have a very, very quick question. I just wanted to know if this testing that you showed in this example, was it by pool of saliva?
Saliva, and we pooled it. There's a whole
Okay.
different issue there with pooling. We did some of the pooling, and then we had a second test. When the pool was positive, we went to the
Yeah,
individual level, and the reports go back to the individual. Yes, we used that
okay.
technique early on as well.
Thank you.
Yep. Quick question in the back, because I know we're at time.
A quick question as well. When you said that you would remove infected through testing, do you mean isolating the infected, or like would this
That's
person?
what I meant.
Oh,
They-
yes, okay.
There was quarantine housing where those people were not removed permanently from the university, just for the period of 7 to 10 days, they were given quarantine housing and then brought back to the community.
Okay, thank you very much.
I think we're at time. We got a lot of questions in. Again, thank you very much. You were very engaging today. I hope you get a lot out of the computational labs. Feel free to follow up with Stephen and enjoy this last week of this portion of your course. Bye, everyone.
Bye, Joshua.